It's a pleasure to me to introduce my colleague and our British representative from IMPA, Rob Morris. So we'll speak on Kinetically, constrained spin models, and Bootstrap Percolation. Rob.
Cool. Thanks very much. Thanks to the organizers for inviting me, for organizing this nice workshop. So I'm going to tell you about two different models, which you may or may not have heard of before. I'll define both. I'll tell you a connection between them. It's kind of an obvious connection, but really the sort of more interesting connections between them are just currently being explored. So this is the work on Bootstrap Percolation, which has been going on I've been involved in for roughly 10 years. I'll talk particularly about joint work with Bela Bolabash, Ugo Dumoulin-Corbin, Paul Smith, and then very recently we started working with Cristina Toninelli and Fabio Martinelli on applications of the ideas to these kinetically constrained spin models. Okay, so can I get this to work? Right, so first, what is a kinetically constrained spin model? So just in the setting we'll be interested in, we have a small constant p, and we're going to take a p random subset of the lattice ZD. What does that mean? That just means we choose each element independently with probability p. Okay? And then this set is going to evolve over time. So let's give each vertex an independent exponential clock. So it rings at independent exponentially distributed random times. And when it rings, we update the state of x. The state is whether or not it's in the set. Okay? So it's going to be evolving over time. I haven't told you how it updates. So what's the update rule? This is the complicated bit. So far everything's very simple. So in general, let U be an arbitrary finite collection of finite sets in the lattice, not including the origin. So we initialize by taking at time 0 our set is A, and then when the clock of a vertex rings, we look at its neighborhood defined by this family U. So if one of the sets in U shifted by x is entirely, I'll call it infected at time t, so AT is the infected sets at time t, then we update, meaning what? Meaning we just re-evaluate, so we forget what state, whether that vertex is in A or not, we put it in A with probability p, and not in A with probability 1 minus p. Okay? We call this a U kinetically constrained spin model. So some examples of families that you should think about. So in the general case, it's a bit hard to think about. So let me give you some special cases. I was hoping to fill the entire board with these, but there's not as much space as I thought. So example 1 is the East model, which I'll talk about a bit on the next slide. And that has the family, so this is in one dimension. And the set U is equal to a single set x, which is the single set minus 1. So what does that mean? So initially you have this random set A. And how does it evolve over time? Well, the clocks are ringing. When this clock rings, nothing happens. It's only when a clock rings, so perhaps I'll draw in the spare ones. When a clock rings and the guy to the left is infected, then you re-evaluate this guy. So you update the state of this guy by infecting with probability p. Okay? So most of the time you don't do anything, but when his clock rings with probability p, sometimes you infect. Okay? And then most of the time, this guy will just disappear again. But sometimes you'll get a situation like this, you'll get a few in a row, and then maybe something different can happen. Maybe this guy could be deleted. Okay? So this thing evolves to the right. And what would we like to know? We'd like to know how long it takes to forget your initial state, which is a kind of complicated question. So let's ask a slightly simpler version of the same question. How long does it take to infect a typical site? Typical site is the origin. So what does the origin see? Let me draw this picture again. So here is the origin, 0. How is this guy going to be infected? Well, you can't, no guy infects anyone to his left, so it doesn't matter what happens to the right. It only matters what happens to the left. So what he cares about is he sees a guy to the left, and this guy has to somehow spread out, infect, until he infects this guy. Right? And this distance is typically 1 over p. Right? So how long does it take? Well, one way is just to keep infecting things until you've infected everybody. But then, so one way would just be literally infect everybody until you infect this guy. But then you've got 1 over p infections in a row. And note that, so an important observation, this update rule doesn't change the distribution. So at all times, the distribution is just the same as the original distribution. Of course, different times are correlated with each other, but the distribution is always just Bernoulli density p. So this is super, super unlikely. So this would take a really long time, sort of p to the 1 over p to the minus 1 over p time to occur. However, there's a better way to do it. What you can do is you infect, so let's suppose we infect this guy. Now infect, let's see, both of these guys, then disinfect this one and disinfect this one. So we've got to distance 3 and we haven't infected too much. Now sort of repeat it by infecting some guys here, and then infect these guys and then remove these. So you can sort of move this guy across, deleting things as you go. By doing this, you can infect the origin only infecting about log 1 over p elements any one time. So it costs you much less. So in physics terms, the energy barrier is much lower. Okay, so it turns out the answer is not p to the minus 1 over p, but p to the minus log 1 over p, roughly. Okay, so this is the sort of thing we're studying. Let me have a slide about that. So the slide's going to say exactly what I said. So the East model, it's one-dimensional. The update family is just a single set. So you update if you can update if the guy on the left is infected at time t. So how long does it take to forget the initial state? Well, you have to, to answer this question, we'll have to define what we mean by forget. So let's not think about that. Let's think about the simpler question that everyone understands. How long does it take to infect the origin? So let's define this tau just to be the minimum time at which the origin is infected. Some random variable of the process. Okay? So this was studied by Chung, Diaconis, and Graham, and Aldous and Diaconis, who proved bounds of this form with a constant, different constants in front, and then the constant was finally determined by Cancrini, Martinelli, Roberto, and Toninelli, who were the first to study actually these kinetically constrained models in the generality that I stated on the previous slide. So this is just one result of many in this paper. It's an extremely, extremely nice paper. So they determine the constant, and it really is this p to the log over p times 1 over 2 log 2. Okay, this is already sort of a highly non-trivial theorem. So what happens in general? So let me give you, I don't have so much space. So let's consider another example in one dimension. So the R neighbor model. Just to see that very different behavior is possible. So the R neighbor model means, so let me just do the case d equals r equals 1. So your u is either -1 or +1. So there's two sets, the guy to the left, the guy to the right. So you can update yourself if either the guy on the left is infected or the guy on the right. Okay? So what happens in this model? What happens to a guy who's infected? Well, he can infect the guy on the left, and then maybe that guy disappears next, or maybe he disappears next. Maybe he disappears next. So with some chance, he just moves left. And similarly, he might then infect this guy and then be infected. He can move right. So all he's doing is just basically a simple random walk. And it has rate something like p. So it'll take him polynomial in p time to infect the origin. So the answer for this guy is not p to the log 1 over p, it's just p to the constant. Okay, so these two very different kinds of behavior in one dimension, or, okay, in these two models. If you can move left or right, then you do this random walk. If you can only move right, then you've got to overcome this energy barrier to get anywhere. So the answer, probably the answer is I don't care, but yes, you can work it out. Yes, in general, it's probably a nice question. So in general, then these really are the two kinds of behavior. So if every rule in your family is to the left, is in the negatives, then you really do have to get across this energy barrier. Whereas if you have a rule that lets you go left and a rule that lets you go right, you can show that it's polynomial. So this is non-trivial but true. Okay, and the talk is basically going to be about a two-dimensional, or an attempt to understand the two-dimensional picture and show that a similar kind of dichotomy occurs. Okay. This is all conjectural, but, well, some parts of it are conjectural. I'll tell you later. Okay. Okay, so when you get to 2 dimensions, this is all in 1 dimension. When you get to 2 dimensions, then things are much more complicated. And so a good way to get started is to think about a simpler model. And that simpler model is Bootstrap Percolation, which is just the monotone version of the model I said. So I'm going to say the definition. It's going to be almost identical, just instead of being able to flip between being in the set and not in the set, once you're in the set forever. Okay, so let me just do it. So once again, P is small. We take a P random subset. You infect each guy with probability P independently. Everyone has an exponential clock. When the clock rings, you update the state. What's the update rule? Well, this part's just the same. When your clock rings, you look at your neighborhood. If one of the sets X shifted by U is all infected, then you just become infected. Okay? So the same thing, except once you're infected, you stay infected. Okay. This is called the U Bootstrap model, and it was first studied only quite recently in general. So Bootstrap Percolation, the particular cases of this have been studied since the late 70s even, and quite intensively over the last 20 or 25 years, 30 years maybe now. But this model only recently by Bollerbash, Smith, and Uzel. Okay, so what did they prove? So they were able to classify these models in 2 dimensions as follows. So I'll say what supercritical and the other definitions mean in a second. So they said that there were 3 possibilities. Either you're supercritical, and it takes time polynomial to infect the origin. This tau star, is for the monotone version. So tau is the real model, tau star is the monotone version. Okay? So either you take polynomial time, or you take e to the polynomial time, or you probably never infect the origin. Okay? These are the 3 possibilities in 2 dimensions. And I'll explain something about why this occurs. So what's the definition? So I need to tell you what stable directions are. So let's think of 2 particular examples again. So I'm going to use the R neighbor model again. So for d equals 2. And R can be 1, 2, or 3. So what is so is it clear what the rule is? You need at least R of your neighbors to be infected in order to be yourself become infected. Okay? So the 1 neighbor rule is very simple. As soon as one guy is infected, he just infects everybody. That's the first case. Okay? Takes you then, you wait for a guy you find a guy who's infected, he takes time, basically linear, to get to you, so it's polynomial. The 3 neighbor rule is subcritical, I mean, basically, you just get stuck immediately. Okay, so you really need density close to 1 in order to infect the origin. The most interesting case is r equals 2, which is critical. And in that case, what you find is that you need to find a critical droplet somewhere, which has size something like 1 over p, which then sort of grows outwards to infect the origin. Okay, and this is the most interesting second case. Right, so how are these things classified in general? We need the concept of a stable direction. So what's a stable direction? So a direction U is stable if when you take the half space, infect the entire thing, then nobody here gets infected. Right? So nobody has enough infected neighbors inside in order to be infected. So we can draw the stable directions on the circle. So what are the stable directions for these three models? For r equals 1, that's what I should ask the audience, but perhaps you're embarrassed. For r equals 1, nothing is stable. Right? Any direction just infects everybody. So r equals 1, it looks like this. R equals 2, anything that's diagonal, there's going to be a guy here who has, it's going to look like a step, right? There's going to be a guy who gets infected. However, this is stable. Right? Anyone here only has one neighbor inside. So these are the 4 stable directions. And for r equals 3, everything is stable. Okay? So this is a very simple case. In general, you can have basically any bounded sequence of closed intervals with rational endpoints as your stable set. But okay, just to see in this simple case. So you're supercritical if there's an entire open semicircle of unstable directions. So for r equals 1, that's clearly the case. For r equals 2, it's not the case. Right? Because every semicircle has one of these stable directions. You're subcritical if every semicircle has an infinite number of stable directions, which in the r equals 3 case is true because everything is stable. But it's not true here because there are only 4 stable directions. And you're critical otherwise. Okay? Okay, so that's the trichotomy. It's very simple and very, very elegant. Okay. Sorry, and I should say that, so Bolabash, Smith, and Uzel proved the parts A and B. They left open part C, which is proved by Ballister, Bolabash, Pruszkutsky, and Smith a year later. Okay. Okay, so we're going to focus on critical models, which from a certain point of view are the most interesting. Let me give you one more example. To think about, which will be important. So the Duarte model has the following rules. So it's also d equals 2. U is going to be, so perhaps I could draw it, this one and this one, and this one and this one. So perhaps I'll actually just write it like that. Is that sufficiently obvious what I mean? So you get infected if either the guy to your left and the guy above you is infected, or if the guy to your left and the guy below you. Okay, so it's, in some sense, a 2-dimensional version of the East model. Okay. And the stable set for this guy is, so to the right is stable, and everything to the left is stable. Okay. This guy is therefore which one of these 3? Well, there's no open semicircle of unstable directions, and there is a semicircle with only finally many stable directions, so it's critical. Okay? So it's in this second family. Okay, so what can we say about criticality, about the critical models? So these are the ones with tau star being e to the polynomial. Okay, so in some sense, the most interesting ones. So we show that. So with Bolabash, Dominikop, and Smith, we show that there's two possibilities. Either you're balanced, I'll say what it is in a minute, and you're really e to the minus alpha, the constant, or you're unbalanced and there's an extra log 1 of a p squared factor. So perhaps just for, and alpha is some number that I'll define in the next slide. So you can see what's happening. Alpha is a positive integer. So what happens in these two models? So r equals 2. So d equals r equals 2. What's alpha going to be? Alpha is to do with how difficult it is to grow, in a sense. So if you take one of these stable directions, like this one, the question to ask is, how many extra infections do I need in order to grow a bit in that direction? And for the r equals 2 case, the answer is just 1. As soon as you find one infection on the boundary, that allows you to get the guy below, and the guy below, and so on. It allows you to get the entire line. Okay? So this is a sort of simple way of understanding the difficulty of this direction is 1. And the same for all of them. Okay, so you only need one extra infection in order to get everybody. And this guy also, as soon as you get one guy, then this rule gives you the guy below, this guy gives you the rule above, you get everything. This one is also 1. So what is alpha in general? What does balanced and unbalanced mean? And which of these are balanced and unbalanced? So in general, you want to know more or less this: how many sites does it take you to get an infinite number going up, and how many to get an infinite number going down? These are alpha plus and alpha minus of a particular direction, of the direction u. The difficulty of the direction is just the minimum of these two, unless one is infinite. So when is it infinite? It's infinite exactly if you're in one of these intervals. So all of this is infinite. And then alpha is just, it's the minimum of a semicircle, so it's the easiest direction to grow, but you have to grow, it's the hardest stable direction to get across to grow in that direction. So the difficulty of a direction is the hardest distance within your semicircle, but you grow in the easiest direction. Okay, so, and so that's the alpha you get in this theorem. So that's the difficulty. So I think that's probably a little difficult to take in, but just to give you an idea of what the alpha is, it's nothing very complicated. It's something you can very easily compute from the family U. Okay, that's all I really want to get across with that. And similarly, being balanced or unbalanced is incredibly simple. It's just whether there's a closed semicircle with the same difficulty. So here, you're balanced because every closed semicircle still has only difficulty 1. But here, you're unbalanced because the only semicircle you can take, you have a chance, is this one, but the endpoints have difficulty infinity. So the endpoints are harder. Okay? So it's just whether or not the endpoints of your easier semicircle are harder or not than you. Okay? So it's just a very simple parameter of the family. Right? Whether or not you really feel you understand it, I hope you agree that it's something very simple. Okay. Okay, well, that's unbalanced. Right? Okay, so we understand very well the situation for two-dimensional bootstrap percolation, these generalized bootstrap percolation models. I mean, this is quite hard to prove, but okay, now we understand it. This was the monotone version of the kinetically constrained spin models. So how is this going to help us with the problem we're really interested in, with the original model? Well, it's not too hard to see, this is pointed out by Cancrini, Martinelli, Roberto, and Tonelli in the same paper, that the U bootstrap process gives you a lower bound on the the time to affect the origin of the corresponding kinetically strained spin model. Right? Because if you always infect, it's natural that you would be easier to then go and affect the origin. Then you can really prove this. So this gives you a lower bound on the time it takes. Okay? So this gives a lower bound for every critical model. So question, when does a matching or roughly matching upper bound exist? Does this really describe what's going on, or is it just completely missing the point? And the main thing that I want to tell you is these two conjectures, which aim to answer this question. So let me try to explain this definition. So we say the family is alpha rooted. So alpha is this parameter of the model that tells you how difficult it is to grow. You're alpha rooted if there are two non-opposite stable directions. I'll draw them like this. Perhaps I mean like this, don't I really? These are the two non-opposite ones. Both of which are, sorry, I think I've done this incorrectly. Really, I do mean this going this way. Both of which it's harder to grow in than alpha. So it means if you're some little droplet like this, it's very difficult for you to escape out of this this cone backwards. It's potentially, well, it must be easier for you to grow this way. Okay? So this is rooted. This is alpha rooted. And if you're not alpha rooted, I'll draw it over here. It tells you something very different. It tells you at the very least, so you might have two opposite directions that are difficult, okay, that are greater than alpha. But you can sort of grow left and right in here with difficulty alpha in this strip. So if you have a droplet here, it should be able to do basically a random walk going left and right in this strip. And, okay, going vertically is harder, but it has a decent chance at least of going in one direction. It should be able to do a random walk. So it looks a bit like, in the one-dimensional case, you remember you could do a random walk for the one-neighbor model. But for the east model, you were stuck to the left and you had to grow right. You had to overcome an energy barrier. So conjecture is that this is the corresponding dichotomy in 2 dimensions. Okay, so if you're alpha unrooted, then bootstrap percolation should give you the correct answer. So this, I've written as conjecture, but I think we basically know how to prove this. So it's currently being written up. And second conjecture, which is sort of implicit in the first conjecture, but I'm slightly more willing to make speculative conjectures than my co-authors. So perhaps you should blame me more than them if this is false. But it seems it should be true that if you're alpha rooted, then you should be able to, in order to get to the origin, because you can't disinfect things so easily, there should be basically an energy barrier. You should have to sort of create these sort of sequence of things, perhaps not growing, but anyway, in order to reach the origin. So it seems very likely that actually the bootstrap will give you the wrong answer if you're alpha rooted. For example, the Duarte model is alpha rooted, and it seems the answer should be p to the minus 2, not p to the minus 1. This seems all conjecture. So first one, conjecture, almost certainly true, and combining some very clever analytic techniques introduced by Cancrini, Martinelli, Roberto, and Tonelli, and then developed further by Martinelli and Tonelli, it looks like adding these things to this bootstrap stuff, then one can prove this. But for the second conjecture, it seems we need more ideas. And I guess I should stop there. Thanks for your attention.